Swayam Prabha. Digital India. Educated India.
Hello friends, so today we are going to start the third lecture on our module number 9 where we are talking about the flow measurement. Now over the previous two lectures we have discussed about quite a few very common options of measuring the flow, like we have discussed exclusively about the obstruction based flow meters where we have several examples like the orifice meter, flow nozzle, venturi meter. In the previous lecture we have talked about laminar flow meter and also something known as the target flow meter or drag force based flow meter. And then we went on to the discussion of so called volume flow meters where we are actually going to get the entire volume flow rate as the output of the measurement, and there we have discussed about two very accurate and common options of high precision based flow measurement like the turbine flow meter and also the electromagnetic flow meter. So today we have several things in our plate. Let me see how much I can go for, because I would like to finish the discussion on this particular topic through this lecture itself. Now in the last class we have finished our discussion on electromagnetic flow meter. Today for this one and also for several other topics I have made my job simple. I have several animation or animated videos to show the working principle, and the first one is related to the electromagnetic flow meter. All these videos are taken from YouTube only, so if you are interested you can go for this. But if I just go back a bit, you can see from the video here on the pipeline we have put two magnetic poles or basically the magnet which are shown, thereby this red and green refers to the two different poles, and this is creating the magnetic field, and the fluid which is coming in a direction perpendicular to this. On the other two arms of this we have put couple of electrodes. So when the fluid is flowing through this, if the fluid has some kind of electrical conductivity, then the one that is just shown, that is the test section, which is basically the flow meter itself. And now you can see the fluid has been shown to comprise of red and blue particles, which basically represents the two different kinds of charges. Let us say red is the positive one and blue is the negative one. Now whenever the fluid is having some kind of electrical conductivity and that is flowing through this magnetic field, then the charges will align just like this. The positive charges will go to one side, the negative charges will go to the other side, and as we have the electrodes positioned on the adjacent walls, then we shall be able to sense this EMF, the potential difference between this, and this EMF will, if we can measure that EMF using some processing circuitry, then we can get a direct measure of this volume flow rate, because the EMF that is being generated, like if V refers to the voltage that is being generated, that voltage has been found to be directly proportional to Q dot. And if we follow the Faraday's law of electromagnetic induction, then the force that is being generated, or I should say the electrical charge that is being generated, that is generally found to be L into B cross V, where L refers to the length of the conductor, B is the magnetic flux intensity or magnetic flux density, and V is the velocity. Both B and V are vectors and it is a cross product. So, we can also write them as L into BV sin alpha, where alpha refers to the angle between them. Commonly we have alpha equal to 90 degree, thereby it is given as LB into V. Generally we also have to add a coefficient S to this, which is some kind of meter based constant which depends on the configuration of the meter. And if we are using uniform magnetic field and uniform velocity, in that case S is equal to 1, but practically that is not the situation. So, we generally have S not equal to 1 for all the practical situations, but that generally comes as a part of the meter specification. So, once we know the magnitude of this B, then we can get from the knowledge of this electric charge or total current that is flowing through, we can get a measure of this velocity of the fluid, or we can directly relate this one to the q dot. Just explained yesterday, this is just an animated view of that. Let us move to the next kind of meter to talk about, and that is known as the ultrasonic flow meter. It is another kind of non-intrusive measurement where we are using ultrasound or sound waves for the measurement. Just see how the configuration is shown here. On two opposite walls of the flow section, we put couple of transducers, like this is one transducer, this is the other transducer, and both act as simultaneously as receiver and detector. Now, if we put certain kind of sound wave from one transducer towards the other transducer, and let us say fluid is flowing, the flow direction is shown here. So, this is the flow direction. Then if suppose c is the velocity of the sound, then v is the velocity of the flow, then the time that is required, or I should say the actual velocity of the wave that is travelling from one transducer to the other transducer will be equal to c plus minus v cos theta, where theta definitely theta depends on the orientation. That means the wave which is moving in the towards the downstream direction, its velocity will be higher. The wave which is moving towards the upstream direction, that is opposite to the flow, its velocity will be lower. If we are talking about theta equal to 0 degree, in that case one wave, the one that is moving in the upstream moving towards the downstream side, that is in the direction of the flow, its effective velocity will be c plus v, and the one which is moving towards upstream, that effective velocity will be c minus v. So, the time taken by the wave to move from one transducer to the other, that will be different, like the one which is moving from, let us say this is transducer 1 and this is transducer 2. So, the one that is moving from transducer 1 to transducer 2, that is actually moving in the direction of the flow. So, its velocity will be increased, effective velocity will be c plus v, and the time taken for this one to reach from transducer 1 to transducer 2 will be lesser. Whereas, the wave which starts from 2 and goes to 1, that is this one, it is moving opposite to the flow. So, its effective velocity will be c minus v, and so it will take more time to reach the other transducer, and from there we can get a measure of the effective flow velocity. Practically the velocity is rated as k into L into delta t, where k is some kind of coefficient related to the meter. L is the distance between the two transducers, that is the path that the wave has to travel, and delta t is the time difference between these two waves going from one transducer to the other. To make it effective, both transducers intermittently works as receiver and I should say source, that is at one instant of time it acts as a source, in the next instant of time it acts as a detector, so that we can get a measurement of this delta t from both from the two combining the two transducers. So, this is the principle of ultrasonic flow meter, again a very effective instrument for measurement of fluid velocities and also a non-intrusive one. Actually, ultrasonic flow meter can be of two types depending upon their working principle, or I should say the ultrasound based flow measurement can be accomplished in two ways. The one that we are showing here, that is known as transit time flow meters, because here we are looking for the time difference required by these two waves to reach from one end to the other. And there is another one which is based upon the Doppler shift principle, but that is generally more used for velocity measurement. So, we shall be talking about that later in today's lecture, because in the Doppler shift principle we get flow velocity, not the flow rate, whereas in this case we are getting the flow rate. Ultrasonic flow meter has several advantages, like the, if I erase these things to make some space. So, they are highly reliable and very high accuracy we can get from them comparably with the electromagnetic flow meter. Insensitive to the pressure and temperature, so we can easily use them for very high pressure situation, very high temperature flows, just like the flow of steam or in a power plant turbine, or maybe the flow of hot combustion gases inside an IC engine, they can always be used for. They are insensitive to fluid properties because we are just sensing the velocity of, or rather time taken by the wave to reach from one transducer to the other, and that does not depend upon any thermophysical properties like density or viscosity of the fluid. Non-intrusive measurement, so it takes into account all the advantages of non-intrusive measurement, hardly any obstruction in the flow, no additional pressure losses, it does not distort the flow itself. It can sense the direction. Clearly, if we do not have any idea which direction the fluid is flowing, still we can get it from the measurement, because as we know, the wave traveling in the downstream direction will move faster, the one moving in the upstream direction will move slower. Accordingly, we can easily identify, just from this two time measurement, we can easily identify which one is the upstream direction and which one is the downstream direction. They does not require too much power for their operation, because they just have to produce the ultrasound wave, and that can be a very low power wave. No pressure losses because of the non-intrusive nature, and they are excellent option, particularly when you are dealing with smaller pipe sizes. Like options like electromagnetic flow meters etc. can be more potent in larger pipe sizes, but this one is excellent for smaller pipe sizes, and very easy to install. We just have to mount the two transducers in suitable location, and mostly that is it. We can go start the measurement immediately. But there are problems, like the velocity, as the time required or the change in time required for the two waves to travel is dependent on the fluid velocity. So, the entire measurement is based upon the flow velocity or the Reynolds number. In fact, it is not a linear relationship that we are going to get from this, it is somewhat non-linear depending upon the Reynolds number. Periodic calibrations are required, and they are not at all suitable for gases, because in gases the sonic velocity will be quite small and may become quite difficult to distinguish that from the gas velocity, or I should say it may become quite difficult to sense the time difference. But for liquid, where the sonic velocity itself is much larger, they are much better option. But even when this liquid flow, if there is some gas bubbles present, similar problem may appear, that is the ultrasound which is traveling through the two phase mixture, if it strikes some bubble, it may get reflected back, and thereby not able to reach the other end of the transducer or the transducer at the other end. So, they are not suitable for gas liquid flows or even particulate flows, flows which are having solid suspensions etc. They are costly, very costly, like the electromagnetic flow meter. For difficult the large pipe sizes, they may be difficult to install, particularly how to orient the two transducers so that we can get a decent travel path, for that may be quite difficult. So, this is the ultrasonic flow meter, which is again a quite common option. All these three that we have talked about, electromagnetic, turbine and ultrasonic based flow meters, all are very standard equipments, easily available from several vendors or manufacturers, and extensive databases available about their performance characteristics. You can easily you can easily look into internet and find a supplier to purchase any of these three kinds of meters of the desired specification. So, there, despite certain disadvantages for each, they are quite potent option and common options for flow measurement. But the next one is a quite innovative one, which is called the vortex shading flow meter. Now, what do we mean by vortex shading? That is, whenever we are putting a blob body, that is a block like this, inside a flow stream, then the fluid has to find a way past this one, that is the flow which is maybe the, if we draw the streamlines which are initially just horizontal lines, they have to find a way around this one. Some of them, or rather one of them, may reach a stagnation point, other has to find a way parallel to this, thereby forming compressed zone of streamlines on either side of the blob bodies. And when they reach the other side, the downstream side of the blob body, there may be flow separation, accordingly the development of recirculation zone, and subsequently the formation of vortex. These vortex are known as the von Karman vortex, based upon the legendary scientist von Karman, who was the first person to properly identify them. This is just an example of how they may look like. On the downstream side, as with increase in the initially we may have, for small Reynolds number we may have a recirculation zone created. However, if we are dealing with a high Reynolds number flow, like in up to this case we are only having recirculation zone and then steady flow. However, if we are dealing with a turbulent flow situation, high Reynolds number flow, then we shall be having this vortex formation. And it has been identified that the frequency of this vortex can give a measurement of the flow velocity. Here the parameter that is of our interest is known as the Strouhal number, St. The Strouhal number is defined as Fs into L by V, where Fs is the frequency of this vortex shading, L is the characteristic length of this vortex shading bar. Like in this case, the D can be the characteristic length. When you are dealing with a spherical object like this, it is very easy, the diameter itself is the characteristic length and V is the velocity. Now, by proper design, it has been found that for several blob bodies the value of Strouhal number can be maintained to be constant over a wide range of Reynolds number. And once Strouhal number is a constant, then the velocity V becomes just L by Strouhal number into the frequency. So, if you can sense the frequency, then it can give a linear relationship to measure the flow velocity and correspondingly the value of the flow rate. Like if we are interested in the flow rate, Q dot will be the cross section area flow into the velocity itself, and if we represent the velocity with corresponding expression for Strouhal number and take d is the object, or sorry, the diameter of the object, the characteristic length, then it becomes pi d cube by 4 into Strouhal number into Fs, that is Strouhal number is constant, K1 into Fs. So, this K1 generally for a given range of Reynolds number with a constant value of Strouhal number, K1 is known, and so just from the measurement of this frequency we can get a measurement of the flow rate. They are suitable for both liquid and gas kind of flow situations, relatively low cost because you just have the blob body to be placed and subsequently you have to sense the frequency, that is all. We do not need to produce any magnetic field or any kind of ultrasonic arrangement, that is why their costs are not that important. Easy to install, hardly any maintenance required over long term operation. Low sensitivity to change in the process condition, that is if there is a change in the process flow temperature or pressure, they are generally not that much sensitive. Stable accuracy and reliability over long terms. Wide temperature range of operation, just mentioned 2 points back, and wide for they can be used for wide variety of pipe sizes. We can change depending on the size of the pipe, we can select different kinds of vortex shading bar and get the similar kind of representation. But they are not suitable for low flow rates. As I have mentioned, when the flow rate is low, then you will be getting, like if I go back to the this particular situation up to low Reynolds number, you are getting only a recirculation zone, no vortex. Only at high Reynolds number, when the flow becomes turbulent, you are getting this vortex, and that is why they are not suitable for low velocity measurement, only suitable for reasonably high Reynolds number. Again perform better for low viscosities, because if viscosity is low, Reynolds number will be high. Some straight pipe length is required to form the vortex, so that you can have a decent upstream portion of uniform flow, then the positioning of the vortex shading bar, and then a subsequent or I should say sufficient length of the downstream section to visualize the vortex and measure the corresponding frequencies. So, quite significant for straight line passage is required. A large pressure drop you can understand, because of the formation of the recirculation zone, all the eddies and vortices that are appearing, there will be significant pressure drop, and that is why again they are not suitable for low pressure drop situation. Where we can't afford large pressure drop, they are not suitable. Possibility of cavitation on the downstream, because of the large pressure drop we may reach a pressure on the downstream side which is lower than the corresponding vacuum pressure, which will lead to the problem of cavitation. Any flow scenario where we are having a large pressure drop corresponding to the measuring instrument, we may reach a situation of cavitation, and that is particularly relevant in this kind of vortex shading flow meter. So, vortex shading flow meter is for high velocities, it is a very good option to have, definitely not as common as the previous three, but is an interesting one, and it is also commercially available. Next we have another very important device, that is called the positive displacement flow meter. Extremely common one, has wide kind of applications because of the wide kind of varieties that we can have. Here the idea is the entire flow is generally divided into several small components. The components are selected such that each of them has a fixed volume. Then just by counting the number of components, we can calculate the total volume flow rate. Like, let us suppose this is the fluid volume that is flowing through. Now we are dividing into several equal components of this and measuring the time required for these components to pass through, or consequently we are measuring the number of components that is passing through over a given period of time. So let us say over a given period of time, over 1 second, only 4 components has passed through. Then the volume of one component multiplied by 4 divided by the time over which this passage has taken place is definitely the flow rate. That is the idea of a positive displacement flow meter. Just like shown here, a positive displacement flow meter can have different categories. We shall be seeing a few examples. The one that is shown here is a gear type. As you can see, there are 2 gears. In the first figure, when the fluid flows through, it is there is no passage towards the lower side, so it flows in the upward direction over the gear. But as the gear is rotating, when it is striking the gear in this portion, it makes the gear rotate, and because of the rotation of this top gear, the bottom one, that is this one, also starts to rotate in the, while the top one, both top one is moving in the clockwise direction, the other bottom one is moving in the anti-clockwise direction because of their arrangement. Now as the top gear moves a bit, then look at the second situation. Here there is hardly any gap left on either side, and so a fixed volume of fluid has got trapped on top of this first top gear, and there is fluid flow now allowed towards the lower side. And as it keeps on moving, or as both the gears keeps on moving, then after some time the top gear releases the fluid towards the downstream side and the bottom gear keeps on rotating, and in the fourth scenario we have reached a situation where there is a volume of fluid being trapped below the bottom gear, and subsequently that is again released to the surrounding. So in one rotation of both the gears, then we can see twice we are collecting a fixed volume of fluid and then discharging that to the downstream side. And now if we know this particular volume of fluid, then we know how much volume we have discharged during one particular movement of this gear, and how many such movements are taking place. That will give you the idea about the total volume that has been supplied. So that is the way we use the positive displacement flow meter. They are extremely accurate. Only way there can be loss is through the small gap which may be there left in this, in between these portions. Generally they are quite tight fit, well sealed through the use of lubricating oils, but there may be small amount of slippage. Otherwise they are very accurate. Can deal with large range of viscosities. In fact, they are more suitable for high viscosity fluid, because higher the viscosity, lesser is the chance of slippage through that gap. So they are more suited for high viscous fluid, but for common fluids or low viscous fluids also they can give quite good performance. Linear scale, because very easy measurement, we know we are just counting the number of such discharges and the volume corresponding to each discharge is given. So it is the final volume flow rate is just a linear function of the number of components that, or number of such collections and discharge combination has taken place. Not too many maintenance requirement, because you can see the one shown here is a simple gear arrangement, so you hardly need any maintenance. No external power required, because the movement of the gear is because of the inertia imparted by the fluid motion itself. So you do not need to impart any additional motion to the gears. Only as the fluid strikes the gears or whatever may be the corresponding arrangement, they start to rotate in the their respective directions, and thereby necessitate the measurement of the flow. Straight pipe section is not necessary, you can put it anywhere, even in the vertical channels also, and they are suitable for high pressure operation. At high pressure we do not have to make any separate arrangement. Of course the slippage may be an issue at higher pressures, but again we present mechanisms or present day industry has sufficient technology to take care of such kind of slippage. and finally they are very reliable over long term. So, this reliability over long term, low maintenance requirement, linear scale, etc., make them very suitable for long term use in different industries, particularly when you are dealing with high viscosity fluids. But they can have a few limitations, like clean fluid is required. If the fluid has certain kind of darts or dust particles or maybe some kind of solid suspensions, then that may block the passage. Like if there is some kind of sand particles or stone pieces are present, that may go into this gear teeth and can block the corresponding passage. So, we need clean fluid. Not suitable when air packets are present or air pockets are present, because if air pockets are there, that will give an erroneous reading to the volume. Actual volume will be less than the volume corresponding to the component itself, corresponding to each component, and there can be significant pressure drop in the flow. So, they are again more suitable for this high pressure operation because of the significant pressure drop to be overcome during the operation. Now, positive displacement machines can be of different kinds depending upon the orientation of this, like the two gears shown here. This is called gear based positive displacement flow meter. Quite often they are also called PD meter or PD flow meter. Here these two gears are looking like ovals, so they are also called the oval gears, and I have a few animations for this. This is for the same scenario, that is oval gear flow meter. The two gears, you can see the gears are connected to each other through the teeth, and as the fluid is flowing, the gears rotate in opposite directions and allow the fluid to flow through. During each motion, you can see a fixed volume of fluid is allowed to pass through. A fixed volume of fluid is collected and then discharged to the outlet side. As the flow velocity increases, you can see the gears are rotating with a higher velocity, but so there are more number of rotations or more number of this collection and discharge, but the volume corresponding to each discharge remains the same. And then there is a counter which counts the number of rotation corresponding to each gear. So, if we count the number of rotation for one gear, then multiplied by 2, we will get the total number of components discharged, and that multiplied by the volume corresponding to each discharge divided by the time of measurement gives you the volume flow rate. So, this is an oval gear flow meter or just oval gear PD meter. This is another interesting one. This oval gear flow meter is generally more used in the lubricating pump of the automobiles. The oval flow meter actually is more common in case of the fuel stations, the gasoline stations. You can see this kind of flow meter commonly. Here, instead of any gears, you have a large plate, just like shown here. You can see this large plate. This plate is mounted on the base on certain kind of hinge, such that they are able to oscillate in their own position depending upon the direction of the flow. And you can see in one case it is allowing a fixed volume of fluid to move on the top side, in the next case it is allowing a fixed volume of fluid on the bottom side. Again, depending upon the flow velocity, its movement can increase or decrease, but every time it is allowing the same volume of fluid to pass through. And now counting the number of components using a suitable counter, which can be a digital one, just like what you can find in a petrol pump. There we can get a measurement of the fluid volume. Another variation that we can have is the rotary vane flow meter. Here we have vanes, we do not have gears or plate, rather you can see vanes. There are several vanes you can find, there are 4 vanes in the one that is shown here, and as the fluid is passing through, you can see this is one particular vane and this is the other vane. So, a fixed volume of fluid gets trapped in these 2 vanes. This is the portion which is separating the inlet and outlet to the flow meter, and now the volume corresponding to one pair of vanes that gets discharged. So, how many number of rotations that has taken place, from there we can calculate the total volume that has been discharged. So, these are called positive displacement flow meter. We can have a few other variations also, like something coming to my mind is called the lobe flow meter, where we have 2 lobes of this kind of shape, somewhat like a dumbbell shape. 2 lobes of this particular shape, and as the fluid flows through this, then the lobes form a mechanism quite similar to the gears. So, this positive displacement flow meter have found extensive application, particularly in conjunction with long term industries or long term operation dealing with high viscosity fluids. That takes us to the end of volume based flow meters. Next we are going to discuss about couple of options for directly measuring the mass flow. Now you may be arguing that if we know the volume flow rate, we also know the mass flow, but problem is mass flow rate m dot is given as rho into q dot, that is density into volume flow rate. So you need to know the value of the density, and if you don't know the density properly, then the mass flow rate that you are going to calculate using the volume flow rate will be erroneous. And there are several situations where we may have non-uniform distribution of densities, so we have to be very careful, and there these mass flow meters can be very effective, where you are directly going to get the mass flow rate as the output. One example is this Coriolis mass flow meter. In case of the Coriolis mass flow meter, we have an U kind of flow section, just like shown here. You can see as the fluid enters from one side of this U and goes out to the other side of the U, the tube is subjected to certain kind of oscillation. The tube oscillates in a direction perpendicular to the flow, and now because of the Coriolis action, I am sure you have heard about the Coriolis action. Like very common example can be the atmospheric or the ocean movement because of the rotation of earth. As the earth is rotated, the air that is travelling on the northern hemisphere and on the southern hemisphere, they take a different turn in different direction depending on the rotation of earth. Same happens to the waves, and which is called the Coriolis action. The same action is used here. Here the tube is oscillating in direction perpendicular to the flow. Now as long as there is no fluid flowing through the U tube, the oscillation is there, oscillation will go on. But when the fluid starts flowing through this, because of the force imparted by the fluid on the tube itself, the tube tries to twist. The magnitude of the twist, if we know the magnitude of the twist, that or the twist angle, that depends on the oscillation and also the fluid velocity. Now the oscillation generally is fixed, because that is something that we are controlling from outside. So this twist angle then becomes only a function of this fluid velocity. This twist, why this twist is coming into picture? Because the direction of this fluid force are different, like shown here. Here it is acting in this direction, here it is acting in the other direction. So accordingly they are trying to twist the tube in opposite direction or move the tube in opposite direction, leading to this twist. Just shown in this animation about the same thing. You can see there is a U kind of configuration where firstly you have one exciter which is exciting the flow, exciting this tube as or making the tube to oscillate. And now as the fluid is allowed to flow through this, these are the couple of detectors which detects if there is any twist at all or not. Now initially when there is no flow, there was no twist, but as the fluid starts to flow through this portion starts to twist, because the force that is acting in this portion and the force which is acting in this portion, they are acting in opposite direction. So they are trying to twist the tube, and from there we can get a measure about the flow velocities. So this is the detector which continuously detects the distance of the tube from its location, or the variation of the distance of the tube from its initial location, and as both we combine the measurement from both the detectors, we can get an idea about the corresponding twist angle. As the flow velocity increases, the magnitude of twist also keeps on increasing. In fact, Coriolis mass flow meter can also give you an idea about the density of the fluid. If we know the velocity, then we can calculate the density from this. Like if the fluid density is higher, the magnitude of twist also will be lesser. If we compare the performance of say oil and some much high density fluid, then the high density fluid, when it is flowing through, that will definitely try to dampen the motion a bit more, resulting in lesser amount of twist. So thereby we can get a measurement of the fluid density as well. So Coriolis flow meters can also be used for measurement of fluid densities. If we just quickly check the mathematical part, when the fluid is flowing through, because of the oscillations that we are putting in and also the fluid velocity, the acceleration of the tube can be written as 2 omega cross v, where v is the fluid velocity and omega is the acceleration. Then if suppose we are having an infinitesimally small element, tube element of mass dm, then the differential force df that is acting on this is definitely dm into the this particular Coriolis acceleration AC. Now, how much can be the mass? If say the rho f is the density of the fluid, then the mass of this corresponding fluid element which is present in this small dm amount of mass is equal to A into dr, where r is a flow section. So, if 2 omega m dot dr. Now, if total length of the tube is L, then total force that is acting on this will become 2 omega m dot L, giving m dot is equal to F by 2 omega L. So, from there we can get a measure about the total mass flow rate. Coriolis mass flowmeters are again extremely accurate instrument for mass flow rate measurement. We are getting a direct mass flow rate measurement which was not possible with any of the earlier instruments. We can also measure density, as I have mentioned, excellent for small pipe sizes. However, they may not be very good option for large pipe sizes, because for large pipes the twist may lead to the breakage of the pipe, but for small pipes we can make them very flexible so that we can have reasonable degree of twist. Non-intrusive measurement, so nothing going inside the flow stream. However, actually we are modifying the flow conduit, so we are not at all going to get all the advantages of non-intrusive measurement, but still we are not intruding anything into the flow stream at least. They can easily operate at very high pressures or temperatures, highly reliable over long term, and no moving part, leading to low maintenance operation. But problem is their initial cost, they are much costlier compared to the venturimeter kind of instruments. They are not feasible for large pipe sizes, as I have just mentioned, because the twisting may lead to the failure of the pipe or rupture of the pipe if the pipe dimension is large or pipe diameter is large. They are not reliable for gas flows, because if we are talking about flow of gas, then the density is much lower. So, the force that is created may be quite small, which is not the case with liquids. Liquids are having higher density, so leads to reasonable degree of twist. So, they are more used for liquid measurement. Theoretically, they can still be used for gas flow measurement, but the low density of gas necessitates a lower sensitivity of the output. Large pressure drop, despite the non-intrusive nature of the measurement, we are having a large pressure drop because we are making the fluid to flow through an oscillating U tube, thereby actually taking it out of its own flow path and then sending it back to the flow path after that oscillating U tube junction, and so there can be significant pressure drop. Presence of dart can affect the reading and because they can clog the small dimension tube, and also there can be significant amount of noise. So, the signal processing is very important in this Coriolis mass flow meter. The other mass flow meter we can have is the thermal mass flow meter. Thermal mass flow meters can have very interesting operating principle. Here what we are doing is that we are allowing some fluid to flow through a duct. At this particular section we are measuring the temperature given by Tf. At this particular section we are again measuring the temperature Tw, and within this portion we are supplying a fixed quantity of heat Q. Then this rate of heat transfer Q dot can be written as m dot mass flow rate into Cp into the change in temperature, that is Tw minus Tf, or I can write m dot is equal to Q dot by Cp into Tw minus Tf. Now, if we can give a constant value of this Q dot and now measure these two temperatures Tw and Tf, we can get a measurement of the mass flow rate. So, that is exactly what that is done in a thermal mass flow meter. Fluid is allowed to flow through this measurement section, and we supply a fixed quantity of power to get a reading about the and take the reading at the of temperature at the inlet section and outlet section, and combining we get the measurement of the mass flow rate. Truly speaking, thermal mass flow meter can operate in two modes. One is a constant heat flux mode, just like shown here. Here we supply a fixed quantity of heat flux or power in the form of Q dot and measure the change in temperature. The other one can be a constant temperature mode, where we control the temperature rise, or for a given TF we can control the outlet temperature TW, and then using some feedback control we adjust Q such that we can maintain a constant value of this TW, and that again in a way gives a measurement of this mass flow rate. Thermal mass flow rates are very suitable for low pressure gases which are not detectable for Coriolis meter. For Coriolis meter, as we have just seen, they are more suitable for liquids, not for gases, and also for only for high pressure gases we may use the Coriolis mass flow meter where the density becomes higher, but thermal mass flow meter are particularly suitable for gases. One problem of course there is a Cp generally we take as constant, but Cp may vary. If the temperature rise is significant, then Cp can also vary. So, if this temperature rise between Tf and Tw is very significant, then we also have to take some corrective factor into equation because of the Cp variation. Now, we are again getting a direct mass flow rate variation. They are particularly suitable in emission measuring tools like pollution emission measuring or car pollution based measurements, etc., and they are medium cost, less costlier compared to the Coriolis mass flow meter, but they are practicable only for gas flows, for not for liquid flows, because for liquid generally specificity is much larger, and if we want to have a detectable value of delta T, then Q need to be much larger. There can be possibility of blockage by dirt or suspended solid because this channel generally have much smaller dimension. Large power requirement can be there, and they can be difficult to calibrate. Still, thermal mass flow meter, because of their relative ease, particularly with gas flow, are quite well used. A variation of the thermal mass flow meter we shall be discussing very shortly regarding the velocity measurement, which is called the anemometer, which uses the same principle but gives a measure of the velocity. We shall be talking about that in just 5 minutes. So, that takes us toward the end of the discussion on flow meters. Just something that I promised in the previous lecture about introducing, that is the use of the obstruction meters in compressible flow. Whatever discussion earlier we have had about the obstruction meters, they are all based for incompressible flows because we use the Bernoulli's equation. But when we are dealing with a compressible flow like gases, there the density does not remain constant. Just if we think about what we did earlier for incompressible flows, there we have seen that for a Venturi meter kind of instrument, the actual flow rate is generally given as CD into area 1 minus beta to the power 4 into 2 delta p by rho whole to the power half, and correspondingly mass flow rate actual CD into rho 2 into A2 or instead of putting the subscript 2, we can just write it as rho. So, if we take the rho inside the equation, then we have CD into A2 beta to the power 4 2 rho delta p whole to the power half. But now, if we are dealing for an incompressible flow situation, this is okay, but if you are dealing for a compressible flow situation, there may be significant change in the value of the density, and there we have to be careful. Careful in the sense here which density to use, that is the first question, and secondly there can be certain other changes in the equation because the Bernoulli's equation itself is not applicable. So, in that situation generally what we do, we incorporate this rho as rho 1, that is the upstream side density, and then we use a corrective factor y. This y is some kind of density correction factor which takes into account the effect of compressibility. So, we are using the upstream density rho 1 in the equation, and then we are using a density correction factor as y. The expression for y for Venturi meters and flow nozzles, we can get such big expression for y. This is actually a theoretical expression. You can easily derive this one following the isentropic flow situation in a compressible flow theory, you can refer to any standard books on fluid mechanics to get the source of this particular derivation. For orifice meters, however, we depend on an empirical relation, some of this particular form, where P2 and P1 are the downstream and upstream pressures respectively. K refers to the ratio of specific heat, that is Cp upon Cv, and beta is the like mentioned earlier, beta is d2 upon d1, that is the ratio of downstream to upstream diameters of the flow measuring section. So, with this corrective factor of y, we can use the similar relations, or we can use the obstruction meters in case of compressible flow scenario as well. I do not want to go to the details of this derivation, this is just to show you what we can do or how we can extend the application to compressible flows just by adding one correction factor. Next, we move on to the next category of our flow measuring instruments, which is velocity probes, where instead of flow rate or mass flow rate or volume flow rate, we are actually getting the velocity as the output. And the first one, you already know about this, the pitot tube, or I should say the pitot tube. In case of a pitot tube, the configuration is shown. We can have two piezometers, one connected on the side of this tube, which is going to give you the static pressure, the other one connected to inside a stagnation point inside the flow domain, thereby giving a stagnation pressure. And so, if you apply the Bernoulli's equation between the two, then on one side you are, if let us say this point is 1 and this point is 2, then you are having P1 by rho V1 square by 2g, or sorry V1 square by 2 plus ZZ1 is equal to P2 by rho V2 square by 2 plus ZZ2. Quite often we can neglect the change in elevation because they are mounted at the same elevation almost, and V2 being a stagnation point, V2 also goes out. Accordingly, V1 square by 2 is equal to P2 minus P1 upon rho, V1 is equal to 2 by rho into P2 minus P1, or we can also write this one as 2 by rho into P stagnation pressure minus the static pressure. So, using just these two piezometers we can get the measurement, or more commonly we can have the pitot tube, where we have both the stagnation part or stagnation probe and static probe mount with each other. We have already discussed in more detail about this one. This is more for academic purpose, because to introduce you to or to let you know that pitot tubes are generally more used for pressure velocity measurement instead of pressure measurement. Next one, a very common instrument is the anemometer, which, as I have mentioned shortly back, it uses the same principle as the thermal mass flow meter, but is used for velocity measurement. We can have two types of anemometers, hot wire anemometer or hot flame anemometer. The idea of anemometer is that in case of an anemometer, we generally have a, if this is your flow stream, we generally mount a small wire inside this flow stream, a very thin wire of very small dimension, small in the sense its diameter can be in the range of just 5 to 10 micron and length of 1 millimeter, and we kept connect this one to some heater, so that a particular amount of electrical energy is passing through this and accordingly producing some I square amount of power. And as the fluid which is passing through this, that will be taken that energy. So, once we reach an equilibrium condition, then whatever electrical energy that is getting dissipated through this particular wire will be taken by the surrounding fluid, so that the temperature of the wire surface that remains constant. That is the working principle of this hot wire anemometer, because the temperature, or sorry, the ability of the fluid to extract heat from this will be governed by corresponding heat transfer mechanism. Now, what is the mode of heat transfer here? It has to be convection, and for convection we know that rate of heat transfer Q dot is equal to some heat transfer coefficient I should say heat flux is equal to heat transfer coefficient due to the temperature difference, and this heat transfer coefficient is a function of the velocity. So, from there we can get a measure of this fluid velocity. Yes. We can have two different modes of this hot air anemometer. Actually, one is constant current mode, just like the thermal mass flow meter, where we are going to supply a constant amount of current, and we shall be having a bridge circuit just shown here, with the probe acting as one of the circuits. This is the probe one, and this is acting as this particular fourth arm of the bridge circuit. Now, whenever there is a change in the temperature of the probe, there will be a change in the resistance. Accordingly, there will be some kind of current flowing through this bridge circuit, and that current will give you a measure of the flow velocity. The other mode can be a constant temperature mode. In that case, we want to maintain a constant temperature of the probe itself. Therefore, whenever there is a gas flowing through this that is extracting heat and trying to cause a change in the temperature of the probe surface, there is a feedback mechanism which is supplied through certain mechanism, maybe the current that is produced, or rather the voltage that is produced in the bridge circuit is sensed by the voltmeter. Accordingly, it activates some heater to maintain a constant temperature at the anemometer surface, and the power that is required to maintain that constant temperature, that gives you a reading of this velocity. Hot air anemometer is the most common one, and that is generally more used for gaseous mediums. However, we can also have hot flame anemometers which are preferred for liquids. In case of hot flame anemometer, we have a quartz crystal, and on top of the quartz crystal we put certain kind of coating. For hot wares, generally we make ware of some noble metal like platinum or maybe tungsten. In case of a hot flame, over the crystal we put a platinum coating, and that acts as the heat producing element. More mechanical strength can be obtained in case of a hot flame anemometer, and that is why we need to make use of that in liquid flow. We can't use a very fine wire of 10 micron diameter like in the hot wire in a liquid flow situation, because that will immediately rupture the wire. So, we have to go for hot flame in liquids. If we quickly try to see how the mechanism works in case of a hot air anemometer, let us say this is our bridge circuit, and the probe, this resistance is R naught, and this is your probe which is having a resistance of Rw. This side is grounded, and now this is the outlet voltage E naught, and on this side we are using a comparator which is comparing the velocity or the difference in voltage between the two sides, that is the voltage difference from this particular end is going to one side, and the voltage from this end is going to the other side, is plus and this is minus. So, this is the voltage that is acting to your source, which is having a voltage of E naught. Now, how much is the electrical current that is being produced? The electrical power, let us say, that is E1. That electrical power will be EW square by RW, where EW is the potential difference that is acting across the probe resistance. Now, how much is EW? EW can be RW divided by R naught plus RW into E naught whole square, that is equal to RW E naught square R naught plus RW whole square. And how much is the current that has power, rather energy that has been withdrawn by the film or the flowing fluid? That has to be the area of the film into H into TW minus TF, where AW refers to the surface area of the wire or your probe, H is the heat transfer coefficient, TW is the surface temperature of the probe, and TF is the fluid temperature, and these two has to be equal to each other. Now, let us assume that H is equal to A plus B root V, which is a quite common way of representing the heat transfer coefficient, or generally we write this as rho into V. because it is dependent on the flow rate. This. So, if we under equilibrium condition, E1 and E2 has to be equal to each other, because E1 is the energy supplied in the mode of electrical heating, E2 is the amount of energy extracted in the mode of convection. So, if we equate these two and write all these expressions together, then we have RW E naught square R naught plus RW whole square is equal to AW to A plus B root rho V TW minus TF. That means E naught square is equal to R naught plus RW whole square into AW divided by RW TW minus TF A plus B rho V. Now, if we are operating in constant temperature mode, then just look at this expression. R naught and RW are constant, because R naught is a part of the bridge circuit, RW is the resistance of the probe itself. So, these two are constant at the design level. AW is the surface area of the probe, so that is also a constant. TF is the fluid temperature, so we do not expect the fluid temperature to change too much. A and B are also constant as per the form of heat transfer coefficient that we have assumed. So, if we are operating in a constant temperature mode, then if that means if we are operating in keeping TW as constant, then what we can write? This one can be written as some C plus D into root over rho V, where C and D are the just the excerpts from this particular equation, and these are constants only. So, we get a relation between this E naught square, that is the power, and the velocity. From here we can get a measure of the total mass flow rate, or I should say we can represent this one, this rho V product, as some function of this E naught square. So, the power becomes a measurement of the total mass flow rate. Similarly, or in alternate way, if we are operating in a constant power mode, we can also get it as a function of the temperature of the probe surface. In that case, this rho V will become some phi prime of this wet surface temperature. So, hot air anemometer is very versatile in use. We can use this one for gas flow or liquid flow, like we use in hot wire mode in gas flow, in hot film mode in liquid flow. Relatively high accuracy, very good dynamic response, so very suitable for transient measurement where there is a significant change in temperature or velocities quite frequently. High spatial and temporal resolution can be obtained. No moving part, just a simple wire or a film, and therefore very less maintenance requirement. Wide velocity range can be covered, starting from very low velocity of laminar flow to highly turbulent flow, we can easily cover by this one. Good performance even at low speeds also, just what I mentioned. Can also be used for mass flow measurement, because just with suitable alternation or very small modification, we can also make this one work as a mass flow meter. They are suitable for long term use and easy to install. But as we are talking about a very small wire in case of a hot wire probe, so they are very fragile, and that is one of the big disadvantage. One problem is this is an intrusive measurement, so they distort the flow pattern. They does not cause that much of pressure drop, but the flow the velocity profile of the flow pattern itself get disturbed. Less suited for liquid flows, but for hot film version can be used, but for actually we have other options for liquid flow measurement. So, hot air anemometer or hot film anemometers are extremely popular for gas flow measurement, but for liquid flow we generally prefer other options. Like very simple, we can go for the obstruction meters like Venturi meters. There can be some pressure drop because of the intrusive nature. They are very fragile, can be expensive depending on which range that you are working with, frequent maintenance requirement, and large power consumption depending upon which mode you are working, constant temperature mode or constant heat flux mode, you always need to supply large amount of power. Despite that, hot air anemometer remains probably the most common option of gas velocity measurement, and you can easily see this one in several laboratories. Like in our laboratory also we have this one, we use this for undergraduate experiments. Finally, I would like to conclude this using two very advanced method of velocity measurement. One is the laser Doppler anemometer. You definitely are aware about the Doppler effect. Like when a car is approaching, like shown here, it is the car with siren is approaching you. It seems that the pitch is higher. When it is going away from you, it seems the pitch is reducing, despite sound is having the same velocity. That is happening because when there is a the source itself is stationary, then all observer hear with the same frequency. However, when the source is moving, the frequency keeps on changing. Like when the source is approaching the observer, there is an increase in the frequency, whereas when the source is moving away from the observer, there is a reduction in the frequency. And this particular effect is used in laser Doppler anemometer, where we supply certain kind of sound wave, and as it strikes the particles present in the flow and that comes back, depending on which direction the particles are flowing, there is a change in the frequency of the particle. That is we use the scattering principle here, scattering of sound waves. Yes. There again very advanced way of velocity measurement, a non-intrusive one, hardly any calibration required. They have excellent spatial resolution and dynamic response, very good accuracy, wide range of particles can be covered with this, and they can easily track high frequency fluctuations. So, even when highly turbulent flow you are dealing with, you can make use of this laser Doppler anemometer, or LDA, which is more affectionately called. Critical power applications like supersonic flows, highly turbulent flows, chemical reacting flows, recirculations, natural convection flows, plasma based flows, multiphase reactions or multiphase flows, this one is conveniently be used. Problem is the cost. There can be noise in the output also. Extensive data processing is required to get the final value of velocity. Optics can be sensitive to vibration. So, these are certain issues, but still it is if you can afford the cost, then this is something that you can always go for very precise velocity measurement. This is a more complete diagram. Here it starts with a laser, then we have a Bragg cell here. The objective of Bragg cell is to split the laser beam into two beams. It acts as a beam splitter. Then it goes through this transmitting receiving optics, and now there are this laser sheet is produced. There are certain particles which are present in the flow. The beam gets diffracted or scattered by these particles, and subsequently they are sensed. There is several as shown in this area, there are several software dominated data processing that are required for the final measurement. If we are looking for one dimensional measurement, then just this particular arrangement is sufficient, but if you are looking for two dimensional measurement, then we need two component probes just like this, which is producing actually 4 beams and giving you 2 velocity components. And if we are looking for 3 dimensional measurement, then we combine 2 component and 1 single component beam like the arrangement shown here, and thereby resolving all the 3 velocity components. An improvement on this LDA is particle image velocimetry, where instead of the scattering principle, actually we use the photographic principle. We produce a double pulse laser like shown here, and that produces a light sheet, and then using some suitable camera like CCD cameras, we get a velocity field, a picture of the velocity field. In case of something I forgot to mention, in case of LDAs, there actually we need certain kind of scattering element. Now, if we are dealing with liquid, there is already naturally sufficient amount of seeding materials are present, but if we are dealing with gases, then we additionally have to seed them using some external particles. And the choice of seeding particle is important because the particles should be light enough so that it can flow with the gas. However, it should also be large enough so that it can scatter the light. Generally, they are of size 1 to 10 micron depending upon what kind of medium you are dealing with. The same is required in case of PIVs also, but here we are not depending on the scattering principle, rather we are taking a picture of the flow field. As the light is falling with this and the particles are moving with the flow stream, with the streamlines, then we can get a proper picture of the streamline itself. PIV is probably one of the most advanced way of flow measurement. It is a non-intrusive one, whole field measurement because we get a picture of the whole flow field, which is not possible with anything else that we have discussed here. 0 to supersonic velocity range we can go for with extremely high accuracy. All the three components can be resolved, several liquids and gases can be covered, and we can get real time image. Just what you can think about a flow field, exactly the same you can get from PIV. Actually LDV and PIV etc., and also the flow visualization, these topics are advanced level topics, not suitable for undergraduate course. That is why I am not discussing at all about the flow visualization, but still I thought about giving a very brief introduction about the LDA and PIV. If any of you are interested, you can go to net. There are innumerable amount of materials available. You can go to YouTube also to see some videos about the working. Just I have to mention for academic purpose, so PIV has disadvantage in the form of complicated computations, but generally when someone purchases a PIV, the corresponding processing circuitry and processing software comes with that itself. High power laser is required, which can be dangerous for live cells. So we have to be careful. Expertise is required both in handling the instrument and also in the subsequent data processing stage, and prediction is dependent on the nature of the seeds. Just to give you an idea, the cost of one proper PIV machine can be easily in the range of 80 lakh to 1 crore. So we are talking about extremely costly technology here, and expectedly they can be very precise in their measurement. So that takes us towards the end of this course. As I have just mentioned, there is another way of flow measurement is the flow visualization in the form of lead-in, shadow graphs etc., but that are part of advanced level discussion. So in a basic level course I do not think we should go there, and so we are restricting ourselves here itself. Then what we have done in this week, we started with a brief discussion of fluid mechanics, Bernoulli's equation, then we talked about different methods of flow measurement. First one that we talked about are the obstruction based meters like venturi meters, flow nozzles, laminar flow meters. Then volume flow meters, several common ones have been discussed like the turbine flow meter, electromagnetic flow meter, ultrasonic flow meter. Today we have also discussed about the vortex shading flow meter and also the positive displacement or so called PD flow meters that we have discussed under this. Then we talked about two different kinds of mass flow meters. One is the Coriolis mass flow meter, a very popular one, and also the thermal mass flow meter. Then we discussed about the use of obstruction meter in compressible flow, just a very brief introduction. Mind you, the principle of this compressible flow can also be used in the pitot tube. The expressions for pitot tube that we use, they are also use the Bernoulli's equation, and so they are applicable only for incompressible flows. But just the way we put a density correction factor in obstruction meters, the same correction factor can also be used in case of pitot tube if we want to use that for compressible flows. So we finished with the discussion on velocity probes, where we discussed about pitot tube, then the anemometry, and then two advanced equipments in the form of laser Doppler principle and particle image velocimetry. So that is the end of this particular module. I hope you have got idea about several very common, starting from very simple to most advanced flow measuring instruments, and I am sure you will find them interesting. Like I have shown a few sample videos here, lots of such videos are available on YouTube. You can search there and get more idea about the working principles, particularly the LDA or the PIV. So that is it for this week. Next week I shall be starting the discussion on another very important parameter for process engineering, that is temperature. Till then, bye.